Hi, and welcome to part 3 of exam 3 for Dr. Koh's transport through exam. In this part, we're going to be looking through and explaining the relationship between the adiabatic saturation temperature and the wet bulb temperature based on the information that we've calculated in part 1, which is the Lewis relationship. Heat transfer coefficient over the mass transfer coefficient is equal to the density times the heat capacity, which we'll also be using in this part of the exam as well as in part 2 where we found the relative humidity between the wet and dry bulb temperatures, which is designated by either partial pressure of water at the surface or far away, depending on which way you want to look at it, divided by the partial pressure of the saturation temperature, which is the vapor part of the pressure at whatever temperature it is at the same location, whether it be the surface or far away from it. And so looking at this equation and what we're dealing with for part 3 of the exam, we have an elongated pipe here that we have transferring water on the bottom of it, as well as air that's going through it as well. And so it's insulated, and the best way to probably look at this is probably by doing starting with setting up a steady state mass transfer equation. And so what we will be doing is that we will be looking at the enthalpy in and the enthalpy out to set up these equations equal to each other. And then we will be able to then relate the adiabatic saturation temperature with the wet bulb temperature based on the information that we have on the inlet and the outlet, as well as being able to cancel out and manipulate the variables and equations in some ways that we would like to, just to make it easier. And so the first place that we're going to start by getting into the part 3 of the exam is that we are going to set up this inlet for the enthalpy. And so this is going to be equivalent to the mass flow rate of the air flowing into the pipe multiplied by the heat of vaporization of the liquid that's going to be transferred through the pipe. And this is going to be multiplied by the partial pressure of water at the first location. So notice that since this is the inlet, this will be over here on the inlet side. I'll mark this as area 1, and I'll mark this as area 2, just to have a quick idea of difference in where we're looking at. So because this is the enthalpy in, we'll be looking at this left side on only the inlet feed, and we'll change that for when we're looking at the enthalpy out for the second location, which will just be the only part of that. And so we want this part to be multiplied by the molecular weight of water, all divided by the gas constant multiplied by the temperature. And so then we will want this to be multiplied by the gas constant and the temperature again. And then we want to have this will be the other part of where on the outside of this equation, these parentheses here at least, this will be the other difference between inlet and outlet. So we'll have the gas constant multiplied by the temperature multiplied by the total pressure, or divided by the total pressure multiplied by the average molecular weight. And then this is going to be multiplied by the heat capacity multiplied by the temperature of the inlet feed. And so this difference and this difference here are the two that will be differentiating between enthalpy out and enthalpy out. Because in reality, and I'll show you this right now actually, where the enthalpy out is actually pretty much the exact same equation. The mass flow rate of the air multiplied by the heat of vaporization. The only difference is that we will be looking at the partial pressure of water at the second location at the end of the pipe. This will be multiplied by the molecular weight of water again, all over the gas constants times the temperature, multiplied by the gas constant times the temperature again, all over the total pressure, multiplied by the average molecular weight. This will also be multiplied by the specific heat capacity and the temperature of the outlet feed. So once again, these are the two main differences between the two, and how we will be probably looking at that for future reference. And so now that we have these, the energy calculations are for the enthalpy on the inlet feed and the outlet feed, we can begin looking at this and canceling and taking stuff out of the equation. So as for right here, for example, the RTs will be canceled out on both sides. The mass of the inlet flow of the air will cancel out on both sides. So we can automatically take these two out of the equation. And so we will be left with here on the left side, or I'll move this over here. It's starting to die on me. Let me get a marker. Just one second. Use this one. Oh yeah, it's a lot darker. Okay. So here on the left side, we'll have the heat of vaporization multiplied by the molecular weight of water, and this will be pretty much all over the this right here, the total pressure multiplied by the molecular weight average. Write that. And this is because we're really just we're condensing this part of the equation right here, just to make it a lot easier and to help it manipulate it more to get what we're trying to find here at the end. And so this is going to be the first coefficient on this left side. This will be multiplied by the partial pressure of water at the first location, multiplied by the partial pressure of water at the second location. And so this will be the left side of the equation, which we'll have at this point, thanks to being able to take out constants such as these two and pretty much relate the partial pressure of water at the first location to the partial pressure of water at the second location. And so on the left side of the equation, we'll be left with the heat capacity multiplied by the temperature change of the inlet feed and the outlet feed, which I will go ahead and change that to T infinity and T at the surface, just to make that easier to look at. Saves me a step on the next part of what we'll be doing. These blue markers are starting to be really crappy. But, oh well. We only got a couple more of these videos left to do. I think I got this one, I got part 4, and then more onto coding. So at least that's will be nice and thankful. So now that we're left with this equation here that we condensed from the equating these enthalpy in and the enthalpy out, and pretty much canceling out certain things that we can, like the rate constant times the temperature and the mass flow rate of the air, we are left with the heat of vaporization multiplied by the molecular weight of water divided by the total pressure multiplied by the average molecular weight is then multiplied by the partial pressure differences of water from the inlet minus the outlet. And this is all equal to the heat capacity multiplied by the temperature difference between the surface and some point far away. So this is where we're at currently and where we got to go from here. Now that we have this part in particular, we can take the Lewis relationship that we developed in part 1 and actually incorporate it into this, where this CP will actually become rho CP. And so this is really just to help keep the units constant. And this was also going to be, well, I guess actually, hold on, this will make more sense. So we'll leave this actually a CP right now, because we're going to be changing the units to get concentration here on the left side. So we will be pulling out this molecular weight times the lambda here for the left side. So we'll have lambda multiplied by the molecular weight of water. And now that we are pretty much going to be change the units and get in the concentration, we'll have the partial pressure of water of 0.1 and 0.2 divided by the total pressure multiplied by the molecular average, the molecular weight average, and that can give us actually is concentration. Those are the equations to give us that. So instead of having this P1 Y1 Py2, or partial pressure of water at 0.1 and partial pressure of water at 0.2 over what would be total pressure times molecular weight, we're just going to instead change those coefficients to concentrations. So we'll have the concentration at the surface minus the concentration at some point very far away. And so now that we reflect this change here on the left side, we can then go and reflect that other change on the right side like we were discussing using the Lewis relationship. So this will become the density times the specific heat capacity multiplied by some temperature difference between some point far away and the temperature point at the surface. And so this is actually a more condensed and better looking equation than the one above. And so the last thing that we're really going to have to do so that we can relate these two temperatures here is that we are going to have to go in and pretty much readjust this equation here so that it's in the form of an ideal gas equation. So we will end up having to divide by the rate gas constant multiplied by the temperature on the left side and the right side, which they'll end up canceling out in the end anyway. But we need to do that so that we can get these partial pressures that are currently being used as concentrations rather into the saturation or partial pressure of the saturated vapor of the water. So in order to do that, we will then need to pretty much there's something we need to do too. I'm trying to think of, sorry. Yeah, so this right here, that's what the other part I was forgetting was. I knew I was forgetting something. So that part right there is also going to have to change, and it's going to be represented in the terms of the P total multiplied by the molecular weight. And then we will also have to multiply by the specific heat capacity. So this equation here is actually going to come up here. And this marker's starting to suck again too. So I'm just going to try to make do with what I got. So the inlet side of this side will now become lambda, which is the heat of vaporization, multiplied by the molecular weight. I hope you can see that. Then this will be multiplied by the partial pressure of the saturated temp of the water at some point on the surface, I believe. And so at the temperature of the surface. That's a better way to differentiate the two. Minus the partial pressure of water some point far away. And so this is going to be what we have to replace that to. And now that we do that, we have to put it in terms of the ideal gas constant again. So we have this RT over on here on the left side. We're going to have it on the right side here as well for what this becomes. So we're still going to have this temperature difference on the right side, which I'm going to put this over here so because this is the one part that doesn't change. I'm running out of space. So that part does not change at all. The only part that will change is this numerator when we start looking at it in terms of an ideal gas. And so that's like I said earlier, where we're going to have to put it back in terms of the total average of the pressure the total of the pressure multiplied by the molecular weight average multiplied by the heat capacity. So now we have it in terms of specific heat capacity in terms of an ideal gas, where we can look at it in terms of the saturated pressure, partial pressure. But these rate constants, or the gas constant times the temperature, they cancel out anyway at the end. And so that's going to help us in, condensing this and really just making it a little neater for one last time. And this is going to finally be, give us our final equation where it's just this top part only, where it's the heat of vaporization multiplied by the molecular weight of water, multiplied by the saturated pressure, partial pressure of water at the surface at whatever that temperature is, minus the partial pressure of water some point far away. So this is going to be the left side. It's going to be all equal to the P total pressure multiplied by the total molecular weight average multiplied by the specific heat capacity, and this is multiplied by the temperature difference between some point far away and on the surface. So this is actually our relation between the adiabatic saturation temperature and the wet bulb temperature, and we can use that even to go back here, pretty much resolve for the relative humidity at the surface, or we could use it again to pretty much, if we wanted to do it someplace far away, we could use the relative humidity and just look at it for some point that's not on the surface instead. We just be rather far away for the partial pressures of the saturated and the unsaturated temps. That one's supposed to be that one. So yeah. And that concludes part 3 of exam 3. We only got 2 more portions left. One more where I'll be using the board, one more where I'll be coding. And so I hope to see you stick around for the last 2 parts of the exam. If not, and something's still confusing, go back and try to make a little more sense of it. In the previous videos I explained, one where we found the relative humidity, the relationship using the Lewis relation, and all the way back in part 1 where we use that Lewis relationship for part 2 and even here. So thank you, and I hope to see you in the next part.